Warm welcome to all my dear friends and students. Very good morning, good afternoon, good evening to all of you, and welcome to this DADM, which is Data Analysis and Decision Making 1 course under NPTEL MOOC series. And as you know, we are going to start the 53rd lecture as shown in the slide, which is in the last but one week, which is the 11th week. And this course total duration is 30 hours for 60 lectures, and each lecture being for half an hour. And each week, as you know, there are 5 lectures, each being for half an hour. And my name is Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember, we were discussing about different life type or loss functions. We gave the examples of linear loss functions, which is linear loss functions. Then we discussed that if the linear loss functions are weighted depending on what is the domain or the range of theta values. Theta is basically the parameters, and the parameters can be either scalar or vector. Depending on the range of the theta, the loss functions propensity or the intensity can increase or decrease. And then you generally we initially considered the squared error loss, because for its nice theoretical properties, because under the unbiasedness property, the t suffix n, where t is the statistic which you find out from the sample. If it is the best estimate for theta, that means the expected value of T n is equal to theta, then the square, that means T n minus theta whole square, that expected value which we call as the risk would be equal to the variance, and we try to basically minimize the variance as the case is. So, obviously, it follows the theoretical properties, and hence we are very comfortable using squared error loss. But squared error loss also it can be weighted depending on the weights you want to give. If the weights can be a fixed value like k 1, k 2, as it can be for the linear loss function also, linear loss function. Then the weights for the squared error loss could also be weighted, weights being a function of theta, which is the parameter value which you want to estimate. And then we very briefly consider, these are just giving a picture. So, we considered the 0 1 loss function depending on the values, how different T n is with respect to theta within a certain range, where the range as per the concept of interval estimation is epsilon. So, it can be loss function can be 1 or 0 depending on whether it is out of range or inside the range. Then we went into considering the two interesting loss functions for which Zellner has worked a lot, and one is basically the linear exponential loss function, which is Linux loss function, where one part is linear, another part is exponential. And we considered the linear part or the exponential part are such that if you are trying to draw the along the x axis the difference between T n and theta, which is delta, and along the y axis you draw the loss function, which is the exponential loss function. For values of a greater than 0, overestimation is more penalized than underestimation, because exponential part dominates the linear part, while for on the right hand side in the first quadrant, and in the second quadrant the linear part dominates the exponential part, that which is for a is greater than 0. If a is less than 0, then in that case just the reverse happens, in the sense that underestimation in underestimation linear part exponential part dominates the linear part, and for overestimation the linear part dominates the exponential part. And we discussed the balance loss function. Balance loss function was basically the concept of using goodness of fit and precision of estimation. Precision of estimation was with respect to the alphas or betas, whichever you denote the parameters for the multiple linear regression you want to find out, and what is the precision of estimation for that with respect to either the squared error, with respect to the linear loss function, with respect to either the 0 1 loss function, whatever it is. And the other part is the goodness of fit, is basically once you find out those alpha and beta using their alpha hats and beta hats, which are the estimates, then we use these estimates to find out y hat, which is the predicted value or the forecasted value of y, and then try to find out the loss corresponding to the fact that we are not able to estimate y exactly using y, but we basically estimate or forecast y using y hat. Now, as per Zellner, the loss function or the balance loss function in the case when you both have the precision of estimation and the goodness of it, both would be squared, but we can basically have different variants of this balance loss function, which we will slowly see as we discuss. So, with this we considered, I said that we will consider 3 examples for the Linux loss function, where overestimation and underestimation are unequally penalized and how the picture can be denoted. So, in the initial case we consider the warranty problem of a new product which is being floated by a marketing company or a manufacturing company, and the company wants to find out the warranty life with respect to its customers and how the customers see the set of information which is there with the competitors also. So, if the competitors in actual the warranty life is 6 months, then whether if you give 8 months as case 1, where you are estimating 8 months as the warranty life with respect to 4 months as the warranty life in case 2 from your side, you will find out that in case if the loss function of the prediction is squared error, then obviously overestimation and underestimation are equally penalized. But in the case if it is a Linux loss function depending on the value of A, you have to find out the what ranges of A would best suit your practicality, because in that sense that in case say for example, you initially give a warranty life of 8, obviously people will be more tempted to buy your products, you will gain a market share, but the probability of the products failing before the 8 months, because the actual warranty life is 6 months, would be very high, then there would be a market loss for you, face value loss for you, business loss for you. So, how you basically compensate the initial market share increase with respect to the losses which you will face from the customers as they switch their products, as they may file for a litigation, all these things, how you will basically balance that using either the concept of A is greater than 0 or A is less than 0, that will depend how you see the practicality. In the case if you give a warranty life of say for example 4 months, so in that same case also underestimation or overestimation can be differently penalized, because in this case initially you lose the market share because products being sold by your competitors has a warranty life of 6 months, people will be more tempted to buy that product. But later on when if you are able to basically give products for which your products would be failing after the 4 months, because your warranty life is 4 months and people get extra benefits of this annual maintenance contract. So, obviously, there may be some positive benefit for you. So, how you balance that again will basically be a question how you see it from the practical point of view. So, with this again I will consider 2 examples and come to the concept of multiple linear regression. As a second example, assume a civil engineer is building a dam. So, the dam actual height is say for example 120 feet, and you are building the dam such that the actual value is 120 feet, and in one case you make it say for example 123 feet, and in another case 1, and hypothetically another engineer would have basically given a height of say for example 117 feet. So, in this both these cases the difference is plus 3 and minus 3. So, for 123 it is 123 minus 120, which is plus 3, and for 117 it is 117 minus 120, it is minus 3. But in one case if you want to basically estimate something to do with the dam's heights or weight or strength parameters, consider using a loss function, and the loss function is quadratic. In that case both the values whether it is plus 3 or minus 3, the overall squared error value would be 9. So, in that case overestimation and underestimation are equally penalized. So, obviously, theoretically it is fine, but let us see it from the practical point of view. In the case if you build a height to 123 feet, so initial cost, man hours, materials, time delays obviously would be there, and you have to basically shelf out more amount of money for that. But consider that a flood comes, or say for example, some huge amount of rainfall happens and the water inundates the banks of the rivers and flows. So, in that case the surge of the water breaching the dam, for which the actual height should have been 120, but you have made it much higher and much stronger 123, obviously the probability would be almost 0. In which case the loss of vegetation, loss of manpower, loss the natural calamity would be much less. So, hence initial cost which was a little bit high or maybe quite high is compensated because you are able to withstand the flood. But in the other case, consider the actual height by the second engineer has been proposed at 117 feet. So, obviously, the initial cost of man, material, labor, time is obviously low with respect to 120 feet. But what happens if when the flood comes, in that case the propensity of the flood to breach the dam is much higher. So, hence later on there may be calamities, catastrophic loss, natural losses, human life lost, cattle lost, vegetation lost, and all the farmlands inundated. So, in that case the overall loss would be much higher than in the first case where you have built the dam to 123 feet or have proposed that to build the dam to 123 feet. So, in both the cases in the practical sense, in the first case when it is 123, in the second case when it is 117, the overall loss would definitely be different. So, you will definitely think of trying to overestimate and build the height of the dam more than 120 feet such that the overall loss is not that much in case when the flood basically inundates or breaches the dam. So, in this case you will basically take a value of A is greater than 0. So, with this I will just read it whatever I said. As a second example, assume a civil engineer is building a dam and she is interested in finding the height of the dam which is being built. If due to some error the height is estimated to be greater than the actual value, then the cost the engineer incurs are mainly due to the material and the labor cost which I said. On the other hand, if the estimated height is less than what it should be, then the consequences can be disastrous in terms of an environmental impact which is in monetary terms can be very high. So, obviously, you will think to have a situation where okay my mistake, in that case you will basically have an underestimation to be more penalized. I made a mistake, it is not A greater than 0, it should be A less than 0. So, it is logical to use a value of A less than 0 in such situations such that the underestimation is penalized more than the overestimation. Let us consider a third example. So, consider that you are making some electrical huge machines, or you have purchased a huge electrical machine which is very sophisticated one, it is costly, and using that machine you basically producing some products in the factory and the workmen work on that. Consider that there is a warranty life for that machine where you need to basically stop the machine and change the vacuum circuit breakers, those trip switches or fuses say for example, and they are very essential to be changed because the warranty life if they are exceeded, there is a high probability that some surge of the voltage would have catastrophic loss on this machine, may definitely affect the production and can have life threatening effects on the human beings who are working on that machine. Consider for example, the actual vacuum circuit breakers or breaker whatever it is, the actual warranty life is 1 year. So, in case 1 you predict the actually should be 1 year, but you basically due to some information set loss you have two cases. In case 1 you predict a warranty life of 14 months which is plus 2, and in another case you basically predict a life of 10 months which is minus 2. So, in the initial case if it is a squared error loss, so obviously in that case 14 minus 2 which is plus 2 whole square is 4, and in the second case which is 10 minus 12 which is minus 2 whole square is 4. So, both the overestimation and underestimation are equally penalized. But let us think what happens in the practical sense. In the sense when if you are using a Linux loss, then in the case when it is underestimated, so what will happen, you will basically stop the production at the 10th month, replace that. So, when you stop that and replace that vacuum circuit breaker, obviously there would be man hours lost, production lost, which is fine. But think on the other hand, in case say for example, if you have not stopped that and basically continued working, then the probability of that surge of the voltage or electrical circuit changes would have a catastrophic effect on the machine. It could have basically burnt your factory, basically could have maimed or hurt some human beings, stopped your production. So, in this case you and in case if you had basically overestimated it, made it at 14, so obviously you would have stopped working on the machine after the 14th month, change the circuit breakers, hence your initial production could have been high, but in case if there is a catastrophic loss, the overall loss because the probability would be much higher because it is 14 and not 12 would have been much higher. So, in this case you will be tempted to take the value of A in such a way that overestimation would be more penalized. So, let me read it as it is written. Finally, to illustrate the significance of overestimation when compared with underestimation, let us consider a different life example. Consider an electrical company manufactures vacuum circuit breakers, interrupters, which are used in as fuses in high voltage circuits or system. As for any product, these circuit breakers have a working life, and it is of utmost importance that these values are estimated as accurately as possible, because it will be used by your customers. In case they are underestimated, then what is its value is in reality, then the consequences is just if they are underestimated, then the consequences would be just labor and man hours loss in terms of production and stoppage time. On the other hand, if the working life of the circuit breaker is overestimated, then the actual figure, then it would definitely signify an exponential form of loss in monetary terms due to accidents or major breakdown of the machineries, or which could have catastrophic consequences. So, for this case of practicality, overestimation would be more penalized, and we will basically take a value of A is greater than 0. Now, we will switch our discussion to multiple linear regression. So, in multiple linear regression is basically a statistical techniques used to forecast or predict a dependent variable y based on a set of independent variables x. So, x is basically a vector. So, if you remember, I did discuss this point, I will try to basically go more in details, not with the proofs, but more of the solutions. So, consider you have you want to predict the temperature, and for the temperature you think that humidity, then pressure, then height at which place you are measuring are the 3 variables which are very important, and consider the wind speed is also important. So, you will basically have x1, x2, x3, x4, where p is equal to 4 are the 4 independent variables which are basically considered in order to basically predict the temperature. Now, obviously, if you remember, we had discussed many of the assumptions based on which we will do the work, assumptions being x1 to xp, where p is the number of random variables, independent random variables which are there for x, which are independent, they are normally distributed, they have a mean value of mu 1, mu 2, mu 3 till mu p plus a variance. Point 1. Point number 2, there is obviously there would be an error, as I mentioned, that error would basically have a normal distribution in the very simplest case with a mean value of 0 and a variance of 1, and the covariance existing between x1 to xp and with respect to individually with epsilon would be basically 0, which means the errors and the random variables which are the independent ones are independent to each other. We will also consider the random variables are independent to each other in the sense that one error does not affect the other, and we will consider that to be true, even though practically that may not be true, but we will consider that to be true in order to basically solve our problems accordingly. So, if you remember those different type of assumptions which you have assumed. So, in order that our prediction of or forecasting is accurate, we ensure that proper assumptions and subsequent calculations, that the errors of prediction the forecasting are minimized. So, obviously, we will see if you remember what we did was we considered the errors. Error was basically y minus y hat, y was the actual value, y hat is the predicted value. Now, your main aim was basically to estimate the values of the parameters corresponding to x1 to xp, which one basically will denote as beta 1, beta 2, beta 3 till beta p. So, our main task was basically to estimate those parameters, because if the population values was not known, our best way would be to take a sample, estimate those values of beta 1 to beta p, and then try to utilize those hat values, that is beta 1 hat, beta 2 hat till beta p hat, which is the estimated values, use them to basically predict the future values of y, and then compare the errors which are there with respect to the actual value of y and the predicted value or the forecasted value of y. Now, whenever you are trying to do, obviously, you will always ensure that the values of betas which you find out in the long run, the estimated values of beta hats would be exactly equal to beta, and also the variances what we will consider would also be calculated in order to find out the variances of y, which will depend basically on the individual variances of x as well as the variances of the error. So, our model which we will have would be like this, we will come to that. One of the most useful models used in is the squared error loss or ordinary least square forecasting method. Despite squared error loss popularity, it is seen that in many instances the forecasting or prediction losses are not of equal magnitude as I discussed. in the Linux loss function, which implies that using SCL, that is squared error loss, may not give accurate results, but still will basically solve and understand the problem from the ordinary least square or the squared error loss point of view. Now, the general standard form of the multiple linear regression model is like this. So, this is y. So, you want to basically predict or forecast y. Y is basically for the sample is n cross 1 matrix. So, first let me make a blank PPT and then add these values. So, I will add 3 blank slides and then continue. So, the standard form of the multiple linear regression is this: y, which is the independent variable, is dependent on x and then error term. So, if you just note down, which I would like to highlight, note down the size of the vector of the matrix. Y is the size n cross 1, x is the size of n cross p, beta is the size of p cross 1, and epsilon is basically a size n cross 1. So, n cross 1 actually equals to n cross p into p cross 1, which is again n cross 1 and plus n cross 1. So, obviously, the dimensionality is maintained. So, let me. So, we have done that, but still I will repeat it. So, y, this is capital Y is equal to y 1 till y n, x is equal to, this is n cross 1, n cross, I will write down the values. So, for the first variable, you will basically have the datas given here. So, for the first data point, so obviously they will be x 1, x 2, x 3. So, corresponding to that, this one where I am highlighting the 1 comma 1 element is basically the first element of the first random variable, and in this case where which is basically the last element in the first row is basically the first element for the pth random variable. Similarly, the extreme leftmost left down value, which I am now highlighting, which is x n 1, is basically the value of the first random variable, its nth value. Similarly, the last one, which is the cell n comma p, is basically the nth value for the pth random variable. So, these are the betas, beta 1 to beta p, and epsilon 1 are the errors, which is epsilon 1 to epsilon n. Now, based on that, we will basically try to find out the values of beta hats, which will also be a size. Let me write the size here, p cross 1, so it will be n cross 1. Now, when I will just move back a little bit in the sense in the discussion, if when I mentioned that dependent structure of the errors and dependent structure of the x's are independent, actually in the diagrammatic form they would look like this. I will draw it. So, I will draw a panel of 4 diagrams. So, in case if the random variables has the mean value fixed with respect to not changing with respect to time, and the variance also not changing with respect to time, it will be like this. So, mean value is here and the variances are also like this. Now, if the mean value is changing, increasing or decreasing, whatever it is, but the variance is fixed, consider is increasing. But the variance is fixed. It will look like this. In case if the mean value is fixed, but the variance is changing, so something like this. In case mean value is increasing or decreasing, consider it decreasing, variance is also decreasing. So, you will basically have these type of graphs with respect to the random variable which is fluctuating. So, let me go back to the initial slide. So, the squared error loss or the ordinary least square estimate of beta. So, I am just giving you the formulas. So, this will be very easy for you to find out any book and read it. So, what you do is that you find out the errors, square them up, sum them up, differentiate with respect to the betas, put them to individually to 0, differentiation is done with as partial differentiation. As you put them to 0, find out beta 1 hat, beta 2 hat, beta 3 hat, all these things in the vector form, it is as given, as I have highlighted. Let me change the color, I think it will be much easier for you to appreciate. And the corresponding variance covariance for the matrix for the betas, which are the errors. The principal diagonal will be the variance of first with respect to first, 2 comma 2 would be the variance of beta 2 with respect to beta 2, and similarly the last column n comma p would be the variance of beta p with respect to beta p, and of the other diagonal elements are the covariances. So, this is again values. So, you can basically, these are just calculations can be found out in any simple book. We will try to utilize this concept in the later class. So, with this I will end this lecture, and considering that we have another 2 lectures for this 11th week, I will try to wrap up regression as required and just discuss a simple problem for that. Have a nice day and thank you very much.